All right, welcome back, everybody. It is Tuesday, February 18th, and we have an E-Day today, so we will be covering, this is actually lesson 4.5, which is all about counting permutations and combinations. And this is actually a little bit of a double. We've got two smaller lessons to cover today, so go ahead and scratch each of these out. We've got lesson 4.5, and then down here, this is also still 4.5. This is technically the last lesson of the unit. So this is the last thing we'll learn, presumably before the test. That might change concerning the weather on Wednesday, but we'll see. Pay attention to Canvas, look at Canvas, see what happens with that. So 4.5 is all about learning how to find out how many combinations and permutations of something are possible. And they do this under the backdrop of ordering something at Dunkin' Donuts. So this is all about ordering coffee. And you pull into Dunkin' Donuts, you're in your unmarked white van or whatever, and you pull up to the drive-thru and they ask, what would you like for all these options? How many different ways can you order your coffee? So, for cold brew, they have three sizes. They have small, they have medium, they have large. They also have two different varieties of dairy over here. We have cream or no cream, and they have two sweetener options. So we have sugar or none. And so we want to find out how many different possible combinations of these are there to make a cold brew, to order a cold brew. Because we have three different sizes, we have two different options for dairy, and we have two different options for sweetener. One way we can do this is to make a tree diagram, just like we made with the general multiplication rule. So we can have a starting point, this decision point, where we make our first choice, and that would be a small coffee, a medium coffee, or a large coffee. Well, from that starting point, now it branches off from each of these into two different options. Because after we order the size, now we pick our dairy. So cream or no cream, I'm just going to say C or NC. All right. So now we have our cream option or our dairy option. And now we're going to pick our two sweetener options. So from each of these, we're getting pretty small here. It's going to branch out into two. And so this would be sugar, no sugar, sugar, no sugar, all the way down. So each of these ending branches represents one possible way to make a coffee, a cold brew at Dunkin' Donuts. Right here, this would be no sugar, no cream, and a medium cup. This one would be sugar, no cream, large cup. We could have sugar, cream, small cup, right? Each branch is a different possible combination. Well, combinations can really be thought of, instead of having to make this giant tree diagram every single time, we can instead think of it, I like to think of it as slots. So I'm going to make three little slots, and each one represents one of our options. This first one represents all the choices we have for size. The next one represents all the choices we have for dairy. And then the last one represents all the choices we have for sweetener. Well, we had three different options for size. We had two different options for dairy and two different options for the sweetener. Now, the whole point of this, what's called the multiplication counting principle, is if I want to know how many combinations there are of something, I can just multiply all of my options together. So 3 sizes times 2 dairy options times 2 sweetener options would be 12 combinations in total. So 12 different ways. We can apply that down here. For a normal coffee, They have 4 sizes, they have 7 dairy options, 8 flavor options, and 2 sweetener options. So to find out how many different ways to order that coffee, we can make a slot for each one. So size, then we have dairy, then we have flavor, then we have sweetener. So now we have 4 different slots: size, dairy, flavor, sweetener. And we have 4 sizes now. We have 7 dairy options, 8 flavor options, and 2 sweetener options. So if I multiply all those together, I will need my trusty calculator for this. 4 times 7 times 8 times 2 is 448 different ways to make a coffee. All right. So, like I said earlier, imagine, we're in our unmarked white van. We've all piled into it as an entire class, and we're taking a class field trip to Dunkin' Donuts. We pull through the drive-thru, and we are ordering, and they offer us a promotion. So at the checkout, we've got 2 big promotions. We can win free coffee for life. So we can use each of the digits 1 through 6 only once and create a 6-digit passcode. If we enter the passcode online and it matches their secret passcode, we will win free coffee for life. Our concern here is how many different passcodes are possible. So if we think about this, we've got the digits 1 through 6. We're going to use each of them only once. So what that corresponds to is we actually have 6 different slots. 1, 2, 3, 4, 5, 6. We have whatever we put as the first number, whatever we put as the second number, whatever we put as the third number, all the way down. Well, what that's going to turn into is for that first slot, we could pick any of these digits, 1 through 6, in that first one. So that means we have 6 different options. Well, what about the second spot? Remember, it says we can only use the digits 1 through 6 only once. So that would be some passcode like 24785 No. It's 1 through 6. 246531. That'd be a valid passcode, right? Because I'm using only the numbers 1 through 6, and I'm using each one only once. So, as I said before, there are 6 different options for that first number, but after that, I can't use that number anymore. So none of the other digits can be 2. So instead, I have 6, and then for the next one, I only have 5 options. I used up one of my options. So it's going to be 6, and then 5, and then, well, now I've used 2 options up, so it's going to be 4, and then I use up 3 options, so next one's going to be 3, and then 2, and then 1. So to figure out how many possible passcodes there are, I just multiply all those together. 6 times 5 times 4 times 3 times 2 times 1. And that gives me 720 different options. Notice on this, we had the same number of options as the number of slots. So I had 6 options in that first slot. I also had 6 slots total. And what that means is in that last slot, we're going to end up with 1. Well, when we do this, when we multiply, starting at a number and going all the way down to 1, this actually has a fancy name in math class, and I'm going to write it out first. So here it is. We write out 6, and then we write an exclamation mark. Now, this number is not pronounced 6. That's not what it is. This is called 6 factorial. So that exclamation point goes with a factorial. And the root word there is factor because we're multiplying all these numbers out. So that's why we call it 6 factorial. And this gives us the number of possible combinations when we have the same number of options as the number of slots. Okay, I also want you to remember that probability of something is equal to the number of desired outcomes divided by the number of total outcomes. And what we've just found is the number of total passcodes that are possible. So if I want to find the probability of winning this game, then I pick one passcode, that's going to be my desired, and then there are 720 different possible passcodes. So that is my probability of a win. And actually, these are not combinations. So forget that I said that. These are not, we don't call them combinations. I'm confusing you for later. I'm sorry. Okay. So the next promotion is win free coffee for a year. So this is slightly not as good as like winning free coffee for life, right? This is only winning for a year, but it's okay. We're still using the digits 1 through 6. We still have no repeats, but now we're only making a 4-digit passcode. So we're going to enter that passcode online, and we're going to see if it matches the secret passcode, and we'll win free coffee for a year if we do that. And so we want to know how many different passcodes are indeed possible here. So since this is only 4 digits, we only have 4 different slots. So 1, 2, 3, 4. And then we're still going to have in that first slot, we're still using digits 1 through 6, no repeats. So in that first spot, we're still going to have 6 options. In the second spot, we're still going to use up one of our options, and we're going to have 5 left. And then we're going to have 4 left, and then we're going to have 3. The only difference here is we're not going all the way down to 1. So this, I mean, really, you could just do 720 divided by 2 since we're no longer multiplying by 2 over here. But 6 times 4, 6 times 5 times 4 times 3 is 360. So there are 360 different passcodes for this one. All right, so what's different about this one is we have less slots than we have options. And that's going to change the math a little bit as we see. So up here, 6 options, 6 slots. We had 720 different possibilities. And then over here, 6 times 5 times 4 times 3, we have a little bit less possibilities because we have less slots going on. So when we have less slots than the number of options, the fancy math name for this is not a combination. We're going to learn what a combination is later. The fancy math name is actually called a permutation. Permutation. So the way we write this out is we write out the word permute, and then the number of options comes first. So we had 6 options, and then after the permute comes the slots. So we had 4 different slots to put everything in. So we would say 6 permute 4 for this. We had 6 options over 4 spots. 6 permute 4 different possibilities. The symbolic way to write that is we write it out with a big P in the middle. So this is still pronounced 6 permute 4. It's just we're not writing out the full word in that. So the fancy technical way to do this formula, and I'll show you how to do it in the calculator. You don't have to remember this necessarily. But it's the 6 factorial, so it's the number of options factorial, divided by the number of options minus the number of slots factorial. So in this case, we had 720 divided by 6 minus 4 is 2. 2 factorial is just 2. And so we get 360. The probability of a win here is still 1 over 360. 1 over the total number of possible options that we have. And I guess the last thing to leave off on here is with that symbolic notation. We usually write it out as NPR, and that's not National Public Radio. We say N is the number of options, and R is the number of slots. All right. So on the little notes for this, first thing to remember, we still have our tree diagram. So the tree diagram doesn't go away. We use it to help count sometimes. So we can branch off, maybe go into A, B, or C as the first 3 options, and then maybe the next options are just one thing or not that thing. So D complement. And then to find out the number of possible ways to do this, we could count the number of ending branches here. 1, 2, 3, 4, 5, 6, right? Next is just counting. Multiplication counting principle. So this is where we make our slots. So I call these slots. And we have the number of options in each slot. Number of options. So we'll have some number times some number times some number. And that gives us the total count of how many different ways there are to do something. Okay? Next, we have factorials. So for factorials, that is where we have the same number of slots as we have options. So 4 times 3 times, and they're decreasing by 1 every time. So this is when the options and slots equal the number of slots and when the options decrease by 1. Okay, so that's the factorial, is when we're like using up an option every time and we go down and we write that out as not as 4, but as 4 factorial there. And then lastly, we have this idea of a permutation. And as we're going to learn later, permutations and combinations are different things in probability. So a combination would be that the order doesn't matter. So a passcode of 246531 would be no different than a passcode of 135642, right? It doesn't matter what order they're in. The permutation, it does matter what order. So 246531 would be an entirely different passcode than 135642. So for now, we're just sticking with this idea of the permutation. Next page is for the combination. So the permutation, I'd say it's the easier to understand out of the two, the permutation versus the combination. But that's when we just have like a lower number of slots than the number of options. So less slots than options. Remember to write this out. We do the big P in the middle, and then we have the number of options first and the number of slots second. And then it has a formula. The formula, remember, it's like NPR is how we write it out. So the formula is n factorial over n minus r factorial. For all intents and purposes here, we could do 5 factorial over 5 minus 3 factorial, which would just be 5 factorial divided by 2. Last thing is that any permutation with the same two numbers on either side of the p just equals that number factorial, right? Because if I have 5 options in 5 slots, well, that's just 5 factorial. If I have 6 options in 6 slots, that's 5 or 6 factorial. So if these are ever the same number, that's just a factorial. So a permutation is just a very, or I guess a factorial is a very special case of a permutation. All right. Do you scream for ice cream? The local ice cream shop in Dontrell's town is called 21 Choices. Why? Well, that's because they offer 21 different flavors of ice cream. Dontrell likes all but 3 of these flavors that 21 Choices offers. He doesn't like bubblegum, the butter pecan, and the pistachio. So, a 21 Choices basic sundae comes in 3 sizes. We have small, medium, or large. It includes 1 flavor of ice cream and 1 of 12 toppings. Dontrell has enough money for a small or medium basic sundae. How many different sundaes could Dontrell order that include only flavors that he likes? So this is a multiplication counting principle question. If you want to pause and try it for yourself, I would go right ahead. What this problem is trying to trick us on is this size option. It says there are 3 different sizes at first, but then Dontrell only has enough money for 2 of those sizes. So when we make our slots, we need to remember that. So we have size as 1 slot, we have flavor as another, and then only 1 of 12 toppings. So we have 3 slots, we have size, we have flavor, and we have topping. We're going to multiply what's ever in there. We only have 2 size options because Dontrell can only afford a small or medium. We have, for the flavor, we have 21 flavors total, but remember, Dontrell doesn't like 3 of them. So we're going to do 21 minus 3, and that gives us 18 different options for a sundae that he likes on the flavor. And lastly, the topping, there are 12 different choices. So to figure that out, we'll just do 2 times 18 times 12, which gives us 432 different sundaes. Okay. Dontrell could order a cone with 3 scoops of ice cream instead of a sundae. He prefers to have 3 different flavors for variety, and he considers the order of the flavors on his cone to be important. So Dontrell is considering a chocolate vanilla strawberry. He considers that a different cone than a strawberry chocolate vanilla. He thinks that's important. This is going to tie into what we're about to do next. They want to make this a permutation and not a combination. So that's why the order does matter. So how many different 3-scoop cones with 3 different flavors that Dontrell likes are possible at 21 choices? Give your answer as a number and using NPR notation. So keyword here, Dontrell likes. That means we're still only going to have 18 different flavors. We still have 3 slots. So we have 18. And then we're using different flavors here. So I'm going to subtract whatever flavor I used on this first one. For the second scoop, we only have 17 flavors to choose from. For the third scoop, only 16 flavors. Now, I can multiply that out, and that's fine. 18 times 17 times 16 is 4,896. The problem is sometimes this is going to get a little tricky with how long these can get. We could have like 15 permute 10, and then you're stuck multiplying out 10 different numbers. So the way we fix that is with NPR notation. So we had 18 different options in that first slot, and then we had 3 slots in total. And now I'm actually going to use my calculator, my TI-84, to figure this out for me. So on your TI-84, there are a couple different ways to get to NPR, or the permute button. I'd say the most organic way to get there is with this math key. So under the green alpha key, there's a math key. Go ahead and click that. And we want to go over to the probability menu. So go ahead and click the right to the probability tab. And then NPR is this second option on that screen. So if I hit NPR, we had 18 options in 3 different slots. So 18 permute 3 is 4,896. Bear with me here. If you're on an older calculator, it's going to say like, it's going to be a little different. We'll see if I can view that real quick. It's going to take a little bit of time to load here. Let's see. Wait for it to load. Come on. There we go. All right. So if you're on the older calculator, you get to it the same way. Over to the probability screen. NPR is still second. But now it's a little different because your calculator doesn't do the smaller numbers here that we filled in on the color model. So instead, this acts like how a multiplication symbol would. So you put the N out front, and then NPR, and then you put the R last. So this would be 18, and then we'll do NPR, and then 3. That gets us the same number. Now, the other way to get to that NPR is actually pretty quick. So let's go ahead and switch back. Wait for it to load here. There it is. So the other way to get there is in one of these shortcut screens. So we've already seen the F4 shortcut screen that gives us all the functions. But there is another screen if we hit the green alpha key and then hit, I believe it's zoom? No, it's not zoom. Don't hit zoom. It's the green alpha key and then window. F2 is what it says up here. So green alpha and then window. And then we see NPR is just number 7 on that list. So you can save yourself a couple of taps. Don't have to go all the way to probability by hitting green alpha key, F2, and then number 7. And that gets you the NPR. Your calculator can also do factorials. Remember, factorials can get pretty big pretty quickly. So if I go green alpha key and window, and then I go down to number 9, this is the factorial button. So I actually have to type the number first. So say we wanted to do 12 factorial, number 9, and this is the number of ways there are to sort 12 options into 12 different spots. That is a very big number, 479,160,000. So be careful with these. Your calculator cannot do anything that is 70 or above on the factorial. It gives too big of a number for the calculator to display. If I do something like 59 factorial, it's getting pretty large by the time we get to 59 factorial. These stack up very, very, very quickly. So that was permutations and factorials on the calculator. I think that's good for now. Let's take a look at the second thing for today. A few years back, Wendy's has a takeout bag which said there are 256 ways to personalize a Wendy's hamburger. Luckily, someone was paying attention in math class. We want to see if this is correct. So, Wendy's offers 9 toppings for their hamburgers. and this guy, Mr. Wilcox, he wants 3 toppings. How many possible ways can he choose 3 different toppings if the order matters? So let's say I have 3 slots, right? Because I have 3 toppings. Well, in that first slot, I'm going to have 9 different options. But I can't get ketchup on a burger twice. So I'm going to use up that first option for the second slot. So second slot, we're decreasing by 1. Third slot, we're decreasing by 1. Now, this is where the order matters. So we're considering like an onion cheese ketchup burger to be different than a ketchup cheese onion burger. So 9 times 8 times 7, this is just 9 permute 3, because we have 9 options in that first slot. We have 3 slots total. If I go into the calculator, I can do alpha F2 and then number 7 and do 9 permute 3. And that gives me 504 different options. Awesome. So, next, Mr. Wilcox decides on ketchup, mustard, and onion on his hamburger. So I'm going to label these real quick. Ketchup, we have mustard, and we have onion. We're going to list out all the possible ways that we can put these toppings in order. So, say we do ketchup, mustard, onion, and then we do ketchup, onion, mustard, so we can swap the last 2, right? These are all different possible ways to put them on in order. Then we could put maybe mustard first, so we could mustard, onion, ketchup, and we could do mustard, ketchup, onion, and then we haven't done onion first, so I could do onion, and then mustard, ketchup, and then onion, ketchup, mustard. I think these are all the ways to do it. So, what this was doing was essentially we had 3 slots and we had 3 different options because we only had 3 toppings to choose from. So 3 times 2 times 1 equals 6 different ways to sort these in order. The next one might be a little philosophical of a question. Does the order of the toppings matter? For example, is ketchup then mustard the same as mustard then ketchup? Now, some of you might go, Mr. Hoffman, I think it does matter. And you know, I guess it could taste a little different if you had the mustard on top of the ketchup than the ketchup on top of the mustard. I'll give you that, okay? So for all intents and purposes, for this assignment, if you think it really, really does matter, I'm just going to add this little caveat. We are blending the hamburger. So we are blending this hamburger and we are drinking it as a smoothie from now on. If you think it matters, this is what you get, okay? We're going to blend it together. Now, does the order matter? I don't think so, because whatever we're doing, we're putting the ketchup in and the mustard in, and then we're blending it. So it doesn't matter what order we do that. So we're just going to say no. It's going to taste the same. The order here does not matter. So I'm going to write that order doesn't matter. And when the order does not matter, this is when we use a combination instead of a permutation. So use a combination instead. So, how many different ways can a person order a hamburger from Wendy's with 3 toppings if the order of toppings does not matter? Well, we already found how many different ways we can order if the order does matter. There were 504 different ways. But now we've got to remove all the ways that are just essentially the same option. So, for instance, I could have picked ketchup, mustard, onion, ketchup, onion, mustard, right? We determined that for any 3 toppings we choose, there are 6 different ways to order those toppings. So inside this 504, I have 6 that are essentially copies of each other. So I have ketchup, mustard, onion. I could have, things that aren't on here. So I could have chosen ketchup, mustard, lettuce, ketchup, cheese, lettuce, whatever. For any 3 that I choose, I have 6 copies that I need to get rid of. And the way we do that in math is we're just going to divide by 6. If I have 6 copies of everything, then dividing by 6 is going to account for that. If we do that division, 504 divided by 6, that gives us 84 different ways. So this is called a combination. And all we're doing is getting rid of the repeats, right? If I wrote out all the possible ways to make this list of 3 toppings I could choose, then something like this would have been in the list. 3 of the same toppings ordered differently. So when the order doesn't matter, I can just divide by the number of ways to do something, number of ways to order them. So the way we write this out is we write it with a big C. So instead of a P, now we're using a C. And we're still going to write it as if we had slots and options. So I still have 9 options. I still have, I'm picking 3 of those options, so I still have 3 slots. The only difference is we don't really say like 9 combine 3. The way we pronounce this is actually 9 choose 3. We have 9 different options. We're choosing 3. We want to know how many possible ways are there to do that. And what's interesting about combinations is they are related to permutations, right? Because over here, we just did the permutation divided by 6. So really, and actually I'm going to do this generally before we do 9 choose 3. So n choose r is how we would say this, is actually going to be n permute r divided by r factorial. Because over here we had n choose r, and then we divided by 3 times 2 times 1. Over here, this was just r factorial. So down here, npr over r factorial. If we remember our formula, this was n factorial divided by n minus r factorial. And now we just need to keep the extra r factorial down here. So for 9 choose 3, we could do 9 permute 3 over 3 factorial. Or we could do 9 factorial divided by 9 minus 3 factorial times 3 factorial. So lots of, in the weeds, lots of factorials. You'd have to type this all out. We don't want to do that. So in the calculator, it is on that same screen. So each of the ways I showed you has that as an option. So I could go to math, I could go to the probability tab, and then go to number 3 and CR and do 9 choose 3. And that's going to give me the same number. I could also go back to that green F2 and then go to number 8 this time. And that gets me the same thing. So either way, you'll get 84. Both are the same way to get to the same, or I guess both are different ways to get to the same thing. Okay? So what you're going to do is there's not necessarily, we've got to pick 3. When you go to the Wendy's ordering station, you can pick 0 toppings, you can pick 1 topping, you can pick 2 toppings. So let me do one of these as an example. If I went and I chose 4 toppings, well, I still have 9 options. I'm just choosing 4 this time. So that's going to be 9 choose 4, which I can just do in the calculator. So you're going to get a bit of practice today. 126 different ways to choose 4 toppings. And you're going to fill out this entire table. So we already did 3. 9 choose 3 was 84, right? So up here, you're going to do 9, choose 2, right? Over here, you're going to do 9, choose 8. So go ahead and pause the video, do all these on your own, and then you can resume the video after that. All right, so I just filled this table out. First thing that you may have noticed as you're doing these, if we're choosing 0 toppings, well, there's only one way to choose 0 toppings, right? It's the way where you pick none of the toppings. So that's why n choose 0 is 1. And then maybe you notice this over here, there's only 9 ways to choose one topping out of the 9, right? Because I can pick ketchup. Well, there's only one way to pick ketchup. There's only one way to pick mustard. So all those are only going to be the 9 different ways to do it. Once we add 2 toppings, then it starts, compiling on itself, getting a little bigger than we would expect. We get up to 84 and 126. The next glaring thing is that these numbers actually repeat. So once we get to 9, choose 4, we're going to be like, ooh, I wonder how many ways there are to pick 8 different toppings. But actually it goes down. So it repeats the numbers going down. So 126, 84, 36, 9, and 1. And the reason why this happens is because once we get to a certain spot, like the halfway mark, well, 9, choose 5 is the same thing as 9, choose 4. The only difference, and this is a different way to think about it, is instead of choosing the 5 options to go on the burger, now we're choosing 4 options to take off the burger. And that's going to be the same number of options as there are to put 4 on the burger. So for each one, there's 126. For 9, choose 6, I'm choosing 3 to remove from my burger. So that's going to be the same number as 9, choose 3. 9, choose 7 is the same way. I'm picking 2 to take off the burger. These numbers are going to be the same. That's why 9, choose 9 is the same, right? There's only one way to pick nothing to leave off my burger, just like how there's only one way to pick nothing to put on my burger. So that's why these numbers are the same as they go down. So how many total ways can you order a hamburger? Well, if you add all these numbers up, we are going to get 512 total ways to order. So whoever made this Wendy's thing at the top, they claimed there were 256 ways. Well, they undercounted by half. Maybe they didn't do this side of the table or something, but there are 512 different ways to order a Wendy's hamburger. All right, let's take our notes here. Let's just remind ourselves of the permutations. Permutations are where the order does matter. So this was like, mustard, onion, ketchup is different than mustard, ketchup, onion. When the order does matter, and to write this out, maybe I'll just say like 1, 2, 3 is a different thing than like 3, 2, 1. So a permutation would count these as 2 different options. So this is written out NPR, N permute R, and this is n factorial divided by n minus r factorial. Well, the second thing, now this is combinations. And with combinations, we just learned that the order does not matter. So a combination would look at 1, 2, 3 and 3, 2, 1 as the same thing, because each one has a single 1, a single 2, and a single 3. So this is the difference. It counts differently. It would only count these as one total, whereas a permutation would count these as different objects. So the way we write this out, now we do NCR, where that C stands for choose, because it's like 9 options choosing 3. And it has a bit more complicated of a formula. We just add an R factorial in the denominator there. Remember to get there on your calculator. We are big friends with the green and then the window key. And everything's on 7, 8, and 9. We have NPR, NCR, and the factorial there. All right. Last thing. With combinations, you'll see we're about to do some probabilities with combinations. Combinations really, really lend themselves to probability. And that's because the probability of an event is equal to the number of combinations of that event divided by the number of combinations total. So that relates to our desired outcomes divided by the number of total outcomes. Combinations are a way to find the number of possible outcomes. So let's look at the practice problem. 5.8. How many ways can you set up a playlist? Janine wants to set up a playlist with 8 songs on her phone. She has 50 songs to choose from, including 15 songs by Taylor Swift. Janine's device won't allow any song to appear more than once in a playlist. So, once we use a song, it's gone. It's not going to appear in the playlist again. She has 50 songs to choose from. 15 are by Taylor Swift. How many different sets of 8 songs are possible for Janine's playlist? We're going to assume that the order of the songs does not matter. So, if the order does not matter, that means we're going to use a combination. So that means she's saying a playlist is not different if, one of the songs is at the beginning of the playlist than if it's at the end of the playlist. You're pressing shuffle anyway, so it's not going to matter. So for this, use a combination, and we have 50 songs to choose from in total, right? Because we're not caring if it's by Taylor Swift yet. And then we have 8 different songs that we are putting in the playlist. So 50, choose 8. And we get a rather large number, 536, 878, 650. And sometimes, like I said, these numbers can get rather large. Sometimes we might want to put these in scientific notation. So the way you do that is you put your decimal point in there, and then you count how many places to the left you have to move it until you get to the 1 digit to the left of the decimal. So I moved it right before the 5. So we had 1, 2, 3, 4, 5, 6, 7, 8 different places. That means this would be 5 point, we'll do like 2 decimals, 5.37 times 10 to the 8th. So it's just like when it's times 10 to a negative number, except we're moving the decimal. Well, I guess we're still moving it the same direction. It's just now it is not being moved to the right. It's being moved to be a larger number. So, next is how many 8-song playlists contain no songs by Taylor Swift. So, it mentioned up here, there are 50 songs in total. 15 are by Taylor Swift. So if we take 50 minus 15, that leaves 35 different options that aren't by Taylor Swift. And so since we have 35 options, we can choose 8 of them. 35 choose 8. 35 choose 8. is 235, 35, 820. So 23,535,820. If we wanted to put that into scientific notation, 1, 2, 3, 4, 5, 6, 7. So we could say 2.35 times 10 to the 7th, right? 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. Number 3, suppose Janine decides to let her phone select an 8-song playlist at random. So her phone now is just creating a random playlist out of 8 songs. We want to know what is the probability that none of those 8 songs is by T Swift. So we actually already have all the ingredients for this, because the probability of no Taylor Swift would be the number of playlists with no Taylor Swift divided by the number of possibilities total. So by the number of playlists total. Well, that's just our combinations. We determined there are 2.35 times 10 to the 7 different playlist combinations that contain no Taylor Swift, divided by the 5.37 times 10 to the 8 playlists that do contain Taylor Swift. So let's do this in the calculator real quick. So I'm going to make a fraction. You can do that with the green key and then the key just to the right of that. And on the top, I'm going to put my 2.35 times 10 to the 7. So 2.35. And then the way you can do times 10 to the 7 without having to type all that out is you can do the blue second key and then the key that is just above the 7. And that adds the E. Remember, E just stands for times 10 to the, so I'm just going to type 7. And then on the bottom, we had 5.37 times 10 to the 8. If I do that, I get 0.044. So 0.044. So there's about a 4.4% chance that we get a song with, or a playlist that contains no Taylor Swift at all. Finally, number 4, find the probability that exactly 2 of the songs on the playlist are by Taylor Swift. So what we need is to find the number of combinations of these playlists that have exactly 2 Taylor Swift songs. What that's going to involve is actually 2 different combinations. So the first combination, we have 15 Taylor Swift songs, and we're choosing 2 of them to put into the playlist. And then after that, we need 2 songs to be by Taylor Swift, but we also need 6 songs that are not by Taylor Swift. So as we talked about earlier, there are 35 different songs with no Taylor Swift, and we need an 8-song playlist. We've already used 2, so that means we're choosing 6 out of the 35. On the bottom, we're just going to leave this as 50, choose 8. And your calculator will take this. You do not have to find what these numbers actually are. So in a fraction, I'm going to do my alpha F2, number 8, and then type in what I just wrote down. 15, choose 2, times 35, choose 6, divided by 50, choose 8. And there is my probability of getting an album with exactly 2 Taylor Swift songs, about 31.74%. All right. This was your lesson for lesson number 4.5. This is talking about counting permutations and combinations. There will be probably a WebAssign assignment, so watch Canvas for that. I will see you next time. Bye.